Yes. So, yeah, then thanks a lot for giving me the opportunity to. Does this work? I don't hear myself. So, can you hear me? Okay. Yeah. So, thanks a lot, Mark, for giving me the opportunity to present this DiskArrays.jl package, which is just to start with a quick overview what this package is for. It basically should help you working with data that is on disk and that is larger than fits into your memory, and can also help for working with remote data. It basically has two purposes. I mean, like, it can help people who wrap data formats into Julia packages for implementing the Julia AbstractArray interface for their data sets, and it can help downstream packages, I mean, like analysis packages, to have a unified interface to talk to data that might sit on a remote source or that might sit somewhere on your hard drive. And so as a very quick introductory example on why I think we need DiskArrays.jl. So this is basically what we want to achieve. And here I take the NetCDF.jl package, which implements this DiskArray interface, which uses it as an example. So we basically just open a data set. This is in a file on my local file system. I open a variable, and after that I can use this data object, which is an object defined by the NetCDF library, as if it was a normal Julia array. And I can use like the Julia indexing, and what I get back is a normal Julia array. And then I do a plot. And in the end, we just, indexing is just one part of the story. I mean, like, if we want to have these arrays that live in some file format on disk behave really like real Julia arrays, I mean, like, indexing is one part, but then we might also just do some computation on it, do some broadcast, compute some statistics, do some reductions along dimensions, iterate over values. I mean, like, and usually that's really what abstract arrays are for. And I don't, since I didn't know which audience to expect, I hope I don't bore you too much. I just do a small reminder of the abstract array interface that is defined in Julia base. And as a quick walkthrough, I just put together an example here where we just define our own array type, and this is done, as you know, quite often in Julia, that when you want to have an array with some special behavior, you usually make it a subtype of this abstract array, which I do here, and I just put together the small example where we have an array that just wraps a normal Julia array, which is here this parent, and which just counts the number of times the array was accessed. I mean, so how often, I just want to count how often did someone read from this array. And all I need to implement here to get a lot of functionality is I implement a method for size, I implement a method for this index style to know if I want to have this array indexed in linear or Cartesian way, and then I implement a getIndex function. But I only need this one method. So I only need this getIndex that has as the first argument my array itself, and then as the second argument the linear index. And yeah, and here I define it in a way that it first increases the access count counter, and then just returns the value of the parent array. Okay. So then I can create my array. Here I make an access count array, and the first thing you see is that I already get a nice show method. So basically all of Julia's abstract array machinery generates me a nice representation of my array that it can be printed. And then I can see that my array, just after calling show, was already accessed 200 times, because show is doing a lot of stuff in the background to find a good representation. What else do I get for free? I get for free broadcasting. I can just add 3 to the whole array. I get reductions for free. I get matrix multiplication with some fallback. And you see that and that all this functionality is basically going through this one getindex function that we have defined, and the Julia array machinery does this for me. We also have a lot of indexing. So getindex is much more complicated than many of us know, and I also learned what is actually possible in Julia indexing when I tried to do this for the disk arrays. So you have these funny things. I mean, like, so with Boolean indices, you can mix them with other types of indices. You can index with vectors of Cartesian index things, and so on. So all this is possible once you have an abstract array. And now, what this all boils down to, or our problem that we have, is this assumption in the abstract array interface that the access to a single element is fast and doesn't have a lot of overhead. Because as you see, when we use this abstract array interface, it's doing a lot of calls into getindex. And this is really something we need to avoid for an array that is stored on disk or that basically lives somewhere in the web, because then we would have to do a request. I mean, like, so for every single access. And so we cannot, which would be the first impulse, just make our disk-based file a subtype of abstract array, because this completely destroys performance. I mean, like, you really cannot work with this file. I mean, like, I think everyone who has tried this, including me, the first thing is you wrap your disk-based array into an abstract array, and then you just hit enter. You want to look at it the first time, and then you see that show already takes 5 minutes to print a representation to the REPL because it's just calling, doing so many C calls. So we have, for disk-based arrays, this significant call overhead, and we typically want to have an access pattern that we read larger portions of the file in a single call at the same time. And solutions to the problem, I mean, like, if you can work with mmap, that's great, and I think many people who do out-of-core things with large arrays use mmap successfully, but many of my arrays are compressed, are chunked, and so on, and so they don't really map to a single contiguous piece of memory, so that's not possible in all cases. One can do caching, but then you also have some overhead, because for each getindex call, you have some kind of dig lookup and so on. So I decided for the most difficult, but then also maybe most rewarding option to basically reinvent this abstract array interface that exists in base, but just based on accessing large chunks of the data. And here's an example for NetCDF.jl, how this is implemented, how we basically use this. This is an excerpt of the code that is in there. I just deleted some stuff that is not important. So basically, NetCDF.jl imports from DiskArrays a few functions. Yeah, I mean, like, this abstract disk array type, and our NetCDF variable, the NCVar data type, subtypes this abstract disk array. That's the first thing we need to do. And then, similar to what we do for the abstract array, there we need to define a getindex to access a single value from the array. And here, all we need to define is this read block function that comes from the DiskArrays package. And this has the signature of, so the first argument is basically the array we want to read from. Then the array, this is a normal Julia array, we want to write to. And this R is basically just a list of unit ranges that denotes the range in the array for each dimension we want to read. So, for example, if this is a 3-dimensional array that sits on disk, the only thing I as a package author that I need to implement is, for a 3-dimensional array, a method that, given 3 unit ranges, for example, give me elements 1 to 10 along the first dimension, 2 to 20 along the second, and all along the third. Just this one method, I can be sure that I get exactly this number of ranges, and I implement this read block function in DiskArrays, which is very similar to the abstract array interface, but here for reading blocks of data. And then, yeah, we just repeat this example. I made it for the access count array, and here I just make an access count disk array according to what we've just seen. So we implement size, we implement this read block for a list of ranges, and we create and we make an access count disk array not just this access count array, but now we subtype AbstractDiskArray. And then you see that similar to the array interface, we also get some behavior for free. So for example, we make this access count disk array, we get a show method. But in contrast to the abstract array, in this case, when we show the array, no data is read at all, because we want to avoid unnecessary lookups into array at any cost. Then, yes?
Maybe you're just coming to this.
Okay.
So now that you... so now that you kind of invent your own interface,
yes.
Maybe this is actually the slide, but doesn't this mean that all the typical indexing and other nice things you can do that relies on the kind of Julia base interface doesn't work anymore, because now it doesn't
exactly.
have it has get block, whatever?
I basically needed to re-implement all the base indexing methods in disk arrays.
Okay, but for example, if I call getindex, I cannot
yes.
do it on your data structure.
Oh, you can. I mean, this is what I'm doing here. So this is all getindex calls.
And then it goes through get
And then
block.
it goes through the disk arrays. The disk arrays, basically, what DiskArrays.jl is doing in this case, it's translating these getindex calls not into single calls into the function, but basically into, it basically reads, in this case, it's reading a bounding box, like the outer bounding box of the data that you have accessed. It's only doing a single call into the read block and returning the values that I actually
okay, thank you. Yeah.
expected. So this is basically what we do. And so we re-implemented, I would say most, I mean, because like base indexing is so complicating, but really a large part of the base indexing machinery is working like here in these examples. And because we only did 3 calls into getindex. So, and in the end, our disk array only got accessed 3 times. But we didn't stop there. We also implemented an own broadcast style. So basically, we can do broadcasting. And here we said, OK, let's do broadcasting lazy by default. So because what we want to avoid at all cost is that you run out of memory. I mean, like, so we never read like the full set of data if the user does not really say that they want it. So basically here we have a lazy representation of the disk array plus 3. And only when we say copy, like you get the result, and then the data is also accessed only once. Like we have reductions, so there are overloads for reduce, map reduce, and which also sum falls back to, so that you can do a sum over a single dimension. You can also do reductions on these broadcasted disk arrays, and so on. So some simple operations work after we implement this abstract disk array interface. To summarize, so package authors implement read block and write block, similar to setindex, getindex for single elements, what you would do for normal abstract arrays. And in return, you get indexing behavior like they are, as it is in the abstract array interface, but while minimizing the number of calls. And currently, this disk arrays is backend for Zarr.jl, for NetCDF.jl, to, let's say, 50% in NC dataset. It's not completely integrated there yet. It's in ArchGDAL for the arrays that you can read from there, encrypt datasets and HDF5 utils. Not yet HDF5.jl, maybe in the future. I mean, there is an open issue, we can discuss this. And in addition to the indexing, you get lazy broadcasting and reductions. And I didn't talk a lot about this, but in the end here, the data is in a serial way. I mean, like in this simple fallback implementation that we have in DiskArrays.jl, it's just serially accessed chunk by chunk so that you never run out of memory when you do your reductions. And so that I would say that's suitable for medium-sized out-of-core arrays, so like some 100 megabytes or something like this. So some things that doesn't fit into your memory. But when you want to do something huge, distributed, you would need to rely on other packages. And so that means other packages can be built on this disk arrays to provide this. What's the time? I just want to, okay, good. Yeah, and since I already said, okay, the data is accessed chunk by chunk, something that I didn't talk about yet is the data chunking. So most of data sets that you find out in the real world actually have, I mean, like HDF5 enables this, NetCDF, Zarr, and so on. They have some internal chunking to optimize access along one or the other axis. So that means your data is basically not, your whole array is not stored like linearly in the array, but you define some internal chunking structure in which data is stored together. And since this is such a common theme, DiskArrays.jl also provides some primitives to talk about these chunks. And going back to NetCDF.jl, I'm like how it implemented this. Basically, when you want to, when you are the package author, I mean like that wraps some data format, you need to implement two methods. I mean like first is this has chunks, so where you basically say, is my data set chunked or is it not chunked? And the second one is an each chunk function, which then basically returns an iterator over all the chunks that my, like of the indices of the chunks that my data set has. And yeah, this, yeah, and okay, that's just the summary. So what happened in our former example, we didn't define has chunks there, so then it defaults to unchunked, so which means it doesn't know the chunks. So whenever it's doing a reduction, it basically just splits the data set along the last dimensions so that it just fits in memory. And when it's doing its loops. So just as a small example, how packages, I mean, like how you can create these chunk types. I mean, like, so DiskArrays, for example, provides this grid chunks object, which is then always making an outer product. So for every dimension, you define the chunks. I mean, like, so as either regular or irregular chunks. I mean, like, depending on if they all have the same size or if they vary. And then you basically make an outer product of it, and then you can just loop through this grid chunks objects when you want to do something serially with every chunk, or you can even do it in a distributed way when you put a PMAP there. So I mean, like, that would be a nice way to work with, for example, when you have a Zarr data set or so. You can, when you are writing downstream code, I mean, like, when you want to work with this, you can, for every package that supports the DiskArray interface, you can open a data set, you can query the chunking structure with this DiskArrays.each chunk. Here we have a very small NetCDF file, so basically that's the whole data fits into one chunk. So that's not chunked, so basically this iterator just returns a single value. But for example, when I open a huge Zarr file from a remote source, I open it just from this URL, and then I call this DiskArrays.each chunk. I basically get here a long iterator of the indices that I could loop over, and I can write code that accesses data in an optimal way. Yeah, so the summary is that, okay, downstream packages can query the chunking structure of any data set through this each chunk function and optimize their data processing pipelines. And just as two examples, both from me, because I mean, for me also the DiskArrays is just a means, I mean, like, to wrap different data. I mean, so we have this YAX-arrays package, which basically has easy parallel map slices-like operations on large data sets. I mean, like, that can just work on any Zarr or NetCDF or so, or a grep data set. And since 1 or 2 years, I'm doing basically a large rewrite because of this, and I'm writing on this DiskArray engine. It's currently more or less a prototype library for doing large parallel moving window operations over huge arrays, using Dagger and so on. But that's still work in progress. It's test registered versions. Some people use it, but I wouldn't recommend it for use yet. An alternative, and I think which is a very low-hanging fruit, because I once did an implementation of this, like in the morning of this, is when you talk about Dagger.jl also has this darray data type, where basically it has an array separated into different chunks, and it's very easy to map basically the chunks of a Dagger darray to the chunks that a DiskArray has on disk. And I think it would be very good to, there's an issue about this, and it would be very good to pick that up at one point anymore, if you're into Dagger and if you really know about what these array types are doing. In order to still allow for a few questions, okay, I would skip this and summarize. We have this DiskArrays.jl package, and as I already said, it's good it's there for two use cases. When you are a package author, when you have wrapped some multi-dimensional package, consider using DiskArrays to implement all the nice array stuff with just a few lines of code. And when you are writing your framework and you want to do some big data analysis on huge arrays, you might depend on the abstractions defined in DiskArrays.jl to get basically to have a lot of sources, data sources. I mean, you've seen the list of packages that implement it, and to basically write code across different data sources. And a big thank you to all contributors to DiskArrays, Felix, Raphael, Alexander Barth, who's constantly pushing for some more special cases, and to everyone else who helped. So thank you.
Okay, do we have any questions? Otherwise, I'll lead with one. Quad first, and then.
Thank you. Thank you for the nice talk. Will this affect the speed of find? Let's say you have an array of strings, really big, it's in disk. Not just numerical, but when it comes to strings.
A string. You have a string. You have an array of strings.
Suppose you have an array of suppose you have a lot of mutations and they have strings attached to them. And with this, you can probably put the entire chromosome in disk and access it. But for each position, you also need to access some kind of string information about that. And it basically, I guess another question is, will there be a disk dictionary equivalent of DiskArray that goes with DiskArray that allows a very fast random access?
So I would say currently not. I mean, so the focus of this is really like on wrapping like the arrays themselves, multi-dimensional arrays.
Gotcha. Thank you so much.
More or less.
Maybe one quick question. Have you benchmarked against using memory map, like mmap, for like uncompressed normal data? Do you know how the performance kind of compares?
I have not benchmarked, but I'm almost sure that mmap must be faster. I mean, yes, okay. I mean, like, so that was not the goal. I mean, like, and I think you cannot reach the mmap performance because like the operating system can do more magic. I mean, like, of course, for you when you use mmap.
And so then you said you re-implement show because you say usually show takes getindex many times and actually getindex is still slow. So now it's fast to do getBlock, but if you call getindex, is still not so fast, if I understood correctly. So then I'm thinking if you have like a linear algebra algorithm, let's say a single value decomposition, which does need to do like there's no way around doing getindex many times. How does that kind of work with your package?
No, I mean, like, so there is. Currently, we have implemented the things that work well, but of course, linear algebra, SVD, or matrix multiplication also, this is not in the scope.
I see. Yeah, thanks.
We're starting to see some two-level chunking schemes with maybe Zarr shards or BLOS, where you have larger files that then contain smaller number of chunks. Mm-hmm. Do you think we need a new interface for this, or can we fit this within DiskArrays?
Okay. I'm like I only know the shards from Zarr. I'm like so they implemented, and there it's a different concept. I mean, like, basically the shards are basically just not as important like performance-wise as the chunks are, because like the chunks are compression units and the Zarr is basically just in the shard as a storage unit, and so I personally don't see a reason yet to extend the interface, because that's really, to me, that's an implementation detail of the respective backend. And so currently I wouldn't see a need to talk about shards here.
Okay, thank you. Are there any other questions?
Yeah, I have one. So I've been using DiskArrays a bit for like a package I'm implementing, but my data is stored as like data records where we have like small arrays, and then the variables are stored in there. So the chunks of the variables are kind of mixed in together. Is DiskArray an okay solution to kind of handle this lazy loading of these variables when the chunks are mixed.
So the question is, if I understand, so it really depends on are the chunks mixed across like also across dimensions? I mean, like, so I'm not 100% sure.
Yeah. So one dimension is in a trunk, and then the other dimensions is like different chunks.
Yeah. So this is not a problem.
Okay.
Yes. I mean, this should work. Yeah. Yes.
Thank you.
Okay. Well, I think if there's no other questions, we'll
Yeah.
move on to the next talk. I think